Okay, so here is Lloyd's algorithm for k-means clustering summarized as we just talked in the previous video. Here we are trying to capture this error term, somehow trying to minimize that. And the way we do that is by using this Lloyd's algorithm, which is an alternating algorithm. As you can see, we begin with these like faded dots here. And this is, by the way, digits data again. So this is the digits data again, and we begin with these like faded dots. So basically beginning with pick centers well separated. So this is that step number one. So these are like well separated centers, and we begin with them and basically assign. So this is like step number one, pick well separated centers, and then update S sub j. So that's like the subsets to be all points that are closest to these mu sub j's. Essentially, I'm picking or assigning all the data to one center or another, depending on their distance from that center. And so I'll have this initial, some kind of initial cluster S sub j. Okay, once I have it, step 3 is to update the actual mu sub j. So basically getting the data from that cluster and calculating the actual center, which is nothing but the mean, right? So this is going to be the mean of my given cluster. As you can see, these like other dots, these black dots, so my centers get updated in that step. And depending on that new center, I will assign my points, let's say x sub n, any point here, to these new centers. And of course, there will be some change of some point going from here to here, some point coming from here to here, and so on, depending on these new updated centers. Might or might not. But this is alternating because first we are picking the centers, assigning the values, and then calculating the centers, and then reassigning the values until En stops to decrease or it becomes like really, really small. That's when we know that that this has converged. And we can actually see that in action here in the digits data. All right, now let's see an application of k-means clustering to radial basis functions network. And you might remember why we're doing that. The first step in a radial basis function network was to find the centers. So my Lloyd's algorithm will help me find that. And on the left side, you're looking at the 10 center RBF network, and on the right hand side, you're seeing 300 center RBF network. All right, so the first thing, as people who already know overfitting, we can tell on the right hand side, overfitting is happening, and this is like huge overfitting, as you can see. So in this like 10 center network, we obtain a really nice classifier, which is this is on the digits data again, and this is obtained after fitting weights using linear regression algorithm for classification. So essentially the problem here that we are solving is digit 1 versus not 1. This is the classification task here. And as I said earlier, here we see a lot of overfitting. And let us assume we want to continue with the flexibility of the 300 center RBF network. One way to deal with that is to go for regularization. And as I said, that the way we've solved it is the linear regression for classification. So that's easier to incorporate, regularization. Or we can use some way of like some knowledge of the problem. We know that there are 10 digits, so maybe 10 center works well, or use cross validation. Either one of those techniques should work fine. Regularization, knowledge, domain knowledge, or cross validation to get the right number of clusters. Regardless, we see the difference between 10 center versus 300 center, and we don't want overfitting to happen, so we have ways to deal with it. But this is the application of my Lloyd's algorithm for k-means clustering to the k-RBF network. All right, the results look good, I mean, for the 10 center at least. Okay, so moving on, the next topic that we will cover under unsupervised learning is probability density estimation. Now, we've looked at this before, the probability density function, and this was an extremely important step in learning, if you remember, because we could actually achieve the first step of learning using some probabilistic analysis that was based on data generation coming from a certain distribution. Essentially, what we were saying was like my data comes from some distribution P of X, and then the prediction that I'm making or the test that I'm doing should also come from P of X. So this fundamental idea leads us to the similarity-based measures, and in specific to the kind of similarity-based measures that we've been talking about until now, is because data and test comes from the same bin, that idea. So this technique comes from that idea because this is a similarity-based technique because we are measuring how likely it is to generate inputs similar to X. Correct? Our learning problem, essentially, how close are we, how close our generated data is to some already given data set, or how close am I able to generate to some given data set. So that's why this notion of similarity comes in when we are talking about probability density functions, and that's how this technique, probability density estimation, comes into picture. Now, the second question that you might be thinking about or asking yourself is, why are we categorizing it under the unsupervised learning techniques? Well, think about it. The probability density estimation is unsupervised because we have like X values, so we are only given data. Hardly we have ever talked about any outcome to those, right? And also that's the first thing. The other thing is, this is also like in some ways a representation of clustering. Whenever we are talking about probability density or probability density function, we are essentially talking about regions of high probability of some data, high probability of the existence of some data. And so that is in some ways, not exactly, but in some ways very close to some clusters, right? And so that's why we're saying this is a softer or a finer representation of clusters. And this is why this probability density estimation technique comes under similarity-based methods, specifically unsupervised learning. All right. So how we're going to approach this is that we'll begin with the non-parametric aspect of probability density estimation, and then we'll move on to the parametric one, which is similar to what we did with the RBF networks in some way. So let's begin with that. The first technique that we are looking at is Parsons windows, and this is radial basis function density estimation. Let's see how this works, right? And so this is a simple example that's given to us where we have like 6 data points, 1, 2, 3, 4, 5, 6, 6 data points. And similar to the radial basis functions, we've put like some bumps on these, as you can see, like these. So this blue line is the final curve that kind of joins all the bumps. Like there must be one bump per like point, something like that. And then when you kind of give a final curve on all of them, that's like when you integrate all of them, that's the final curve that you're getting. All right. So like when we put a bump or a curve of some volume, and that some volume is 1 over n, if n is the number of points, then on every point, the volume is 1 over n. Why? Because this represents in some way that this data point corresponds to the probability density contribution on each point. So that's the idea. And then when we add each one of those, or essentially in this case, like integrate over the entire, like the number of points that we have, then each individual bump is normalized to like 1 over n. So when you integrate, you get a 1. So basically, this entire distribution is a normalized probability density. Let me write it down. It's normalized probability density. All right. And so you can think of, like, if you're looking at these curves, you can think of these as like three overall, like three maximas that are happening somewhere. And so they're suggesting like regions of high probability density. So in some ways, like similar to clusters, not quite, but yeah, similar to clusters. Now the estimate of this curve is given by this equation here. This p hat is the estimate, so that's why the hat. And it is given by this particular equation where, now, because this is like a normalized probability density function, we are basically talking about the Gaussian kernel, and the properties are inherited from the Gaussian kernel. So that's what we're talking about here. And so I'm computing the density at point x. This is the estimate for that. And the Gaussian kernel is being evaluated at some xi. R is the scale parameter as always. And so here's the equation. This is how we do the estimate. And so the way this Parsons window essentially works is by estimating for this point x using this particular equation. You can see the Gaussian kernel phi of z is this is the exact equation, but obviously we can compute that using this input parameter. So it's as simple as that. Now let's look at the results. What are the results when we apply it to essentially digits data again? Let's look at that. Okay, so this is the digits data and the RBF density estimate on the left side. So this y and x is, as far as I remember, is the intensity. Again, we're working with the same features, and this was the symmetry. Okay, so this left side is showing us regions of high probability. The peaks here, the peaks are regions of high probability. All right, and so then you might think like, what are these, like the width of each of these, and how is it decided? Well, for the Parsons window, it's decided by the scale parameter, and the scale parameter here essentially has the same explanation as we had in the RBF, non-parametric one. So it's similar to that. So the width is decided by that. Now, if you look at the right side, this density contours, what are these? This is like the view of probability density estimation. So these are contours of constant probability. What does that mean? Well, the right in the right picture, right hand side, the red ones, the dark red ones are depicting very high probability density. Blue is depicting low probability density, and you can actually see the clusters. And corresponding to k-means clustering of digits data, here, this is the equivalent picture of density estimation. Clusters are more readily visible with the smoother Parsons window than the nearest neighbor estimate here. And of course, like this kind of tells us this is the area of like high data density, and so this is like dark red, and the blue ones are like sparse. So this is what this is depicting, this picture. All right, so with this, we saw one technique, which is the Parsons window technique of like density estimation. And now we're moving to something that's known as the Gaussian mixture model. And it's nothing new. Now this Parsons window that is calculating the bump on each data point is similar to non-parametric RBF, I can say. It's similar to non-parametric radial basis function. All right, but then remember, we moved to the parametric one. We found easier to work with, and we found easier to solve. And so we are like moving like in a similar way, I would say, to the parametric side of this model, and that is known as the Gaussian mixture model, or the GMM. Let's see what this is, and then let me write it down. The Gaussian mixture models, and GM. All right, what is this? Well, here, just think about it. Put a bump at k centers, and that's how we kind of create it, like just like we did with the parametric RBF networks. Let me illustrate that with like some data, right? So let's say my data distribution is something like this. Of course, there is data here as well, but then I have some concentration somewhere. And so the way this works is that I have some k decided, right? So this is just an illustration, and let's assume that k is 4. So some centers, we begin with some centers, and those are known as mu1, mu2, mu3, and mu4. And we just like decide this is mu1, mu2, mu3, and mu4. So we have like 4 centers. These are the bump centers. Now, in addition to the centers, not just the centers, but the shape of the centers is also important in this case when we are talking about the Gaussian mixture models. All right, so the shape means like some kind of orientation, rotation, symmetry, those kind of things. And so when we have like these things placed, these bumps placed, the bumps not just have like similar to what we had last time, that they had height. Now this time they also have some kind of a shape. And how do we specify shape like mathematically? Well, we specify shape by using a covariance matrix. So covariance matrix helps us depict their shapes. So let's assume that because we have like 4 centers and then 4 bumps placed on those centers, so we have like sigma 1, sigma 2, sigma 3, and sigma 4. All right. Now, these are the 2 parameters that we are thinking of like having for this data. And then think about like another parameter, which is like, because we are talking about probability density, so we are also concerned about how much data is covered by each bump. And in order to depict that, we use something that's known as bump weights. And as I said, this is similar to like how much data, how many points are there, or like the volume of the data that's covered by each bump. And so we're depicting it by W1, W2, W3, W4. All right. So this is all. This is it to the depiction of a model that has parameters. Essentially, we began with certain number of parameters, that's bump centers, the Ks, and then we picked the centers, and then we specified a covariance matrix to like allow the bumps to have some shapes, and then finally decided the weights, right? And this, by the way, is 1, not 7. Okay, so now what we are going to do is we are going to generate the probability density models using these parameters. That's why these parameters are important, right? You're going to generate the data. That's how the probability distribution helps. So how are we going to generate the data? What is going to be our estimate for this data? Essentially, the estimate for this data is going to be denoted by p hat of x, similar to what we did with the parametric one. And I'm going to write this as like sum it up for all the centers, which is starting from k equal 1. Let's say I have like total big K number of centers, and then the weights of each bump multiplied by the density for each bump. And the density is given by this, I'm going to talk about it, which is a function of the point, the data itself, the center, and the covariance matrix. And this is small k. All right, so this term here is the density for a bump that depends on centers and shape, right? So this is my density. And this entire thing here is like a general formula that computes the probability density, right? This is calculating the probability density. And think of this as a weighted mixture of bump density. Why? Because I have these weights that were like specifying how much data is there in each bump. And then I have some function that defines that density. If I multiply them and sum them up, then this is like the weighted mixture of bump density. And this is essentially my GMM. All right. So why is this my so the mixture model, you can understand that is a mixture of like all these bumps and sum them up with the densities. But where does this like Gaussian word comes in? That is because we're assuming that this n here is Gaussian density, not just density, but Gaussian density. All right. And so because this is like a Gaussian density, this function, and so p hat x is, or it corresponds to the Gaussian mixture model. And so this is my Gmm. This is how I get the estimate of my Gmm. Now, if we further like kind of dig deeper into what this n is, and let me write it here. And essentially, in general, this n, and I'm getting rid of the k's to be more generic. So this here essentially is pointing, the centers are essentially nothing but the mean of this. And this here is pointing to the covariance matrix, the shape, right? This is the covariance matrix. All right. So when you generate data from this density, this distribution, the average or the expected data point will have this mean mu and covariance sigma. This is what this means. And so therefore the Gaussian distribution is given by, and there is like this general formula and certain properties that we might need to use going forward. And so I'm going to write them down. The first property is that this is given by, and this is a known formula for the Gaussian density. is 1 over, and this is, by the way, explained very well in the book, so you can refer to that. I'm just like listing the properties. The covariance square root times e to the minus half x minus mu, where mu is the mean, sigma minus 1 x minus mu. So this is how this is computed. This is how we get it. And if we have like data points x1, x2, x3, and so on up to xm, then any expected data point, like the sum of all those data points or the average of all those data points, converges to this mu, which means the expectation of any point x is essentially mu. So this is not just like the center, but the expected mean. Or like more mathematically, what I'm trying to say is that if we have like data x1, x2, and so on up to xm, then if I like sum this over all m, any data point, this is essentially the definition of the expectation of any x in my data, and this converges to or is equal to mu. The mu, that's the parameter here. And then the other property of the Gaussian density is that if I take the outer product and average it, so the outer product meaning xi psi transpose, this converges to the expected value. This essentially is the expected value of x transpose, right? And this converges to something that's mu transpose plus the covariance matrix. So these are some of the properties that are nice, and they make our analysis easier, and so that's why I've listed them here. All right. So in a more generic format, the final estimate for my model p hat x is, again, I'm like rewriting it from 1 up to k, the weights, and then the probability density, which we know is the Gaussian, k and sigma k. All right. In addition to that, this is like these weights. There is this condition on weights that this should be greater than 0, and the sum of the weights starting from k equals 1 to k should be 1, right? So this is similar to the RBF network with weights wj and like a Gaussian kernel. Essentially, we are trying to get a sum of the Gaussian bumps, and this equation, essentially this particular equation, is based on the generative data model, and the parameters of this model that need to be learned from the actual data are the weights, the centers, and the covariance matrix. This J corresponds to like every, I would say, region, right? So each of these clusters, in another way, we can call them clusters. All right. So we get to pick these because these are kind of like input parameters. So these are nothing but like weights, centers. We get to pick them initially, and shapes. So because we get to pick these, how do we pick them? And how do we pick these to fit the data well? And how do we pick these to get the results well? Now, since this is probability density, so it's pointing towards generating data in a certain way, or maybe picking the parameters in such a way so that we can maximize the probability to generate this data x1, x2, xk, and so on, right? So what we are trying to do is like pick in such a way, right? Pick in such a way that we maximize the probability, to generate the data x1, x2, whatever we have, right? Let's say xk or xm, whichever. Now this overall technique is the maximum likelihood. We have seen that once before, but now we have a better algorithm to sort of get the best weights, the best centers, and the best shapes. And that algorithm, although it's not an exact algorithm, again, it's an alternating algorithm that we're going to look at, and that is known as the algorithm of expectation maximization. And the exact derivation of that algorithm is given in the book, in the appendix, I think, of this chapter. But we are not going to go into the details of the math behind it. Rather, we are going to look at the overall steps and how it helps us achieve this. All right, so let me write it down. This is expectation maximization, but before that, I think we have to talk about some variable that we're going to use. But anyways, I'll still write it. Expectation maximization. That's what we are doing. All right, so this is useful. Why? Because this is a very powerful tool for maximum likelihood. It's an iterative algorithm. It's easy to implement. It's intuitive. So all those benefits come with it. Now, even before we start talking about the expectation, by the way, the expectation maximization is going to come with the discussion of this variable. And so we are introducing this latent variable, which has similar implications as the Lloyd's algorithm had. For example, if we knew which data point belongs to which bump, right, then we can easily figure out, like if we knew, I will write it down, we knew which x of n belongs to which bump, then we can easily get like the centers and the covariance matrix, right? And in some sense, weight will be like the fraction of the data points belonging to that bump. So the fundamental high-level idea is that we'll begin by assuming that we know it, and then we are going to calculate the parameters and improve. So similar to what we did earlier. But now we are going one step further, and what we're trying to do is we're trying to alternate between two different points, and one extra variable will be added, as you will see why. Okay, so what exactly are we trying to alternate between? The first step that we are trying to kind of ascertain or establish is that if we know which data point belongs to which bump j, as we said, we can calculate mu and mu j. Let me make it that. And let's say this is like the first point, of course, because I don't want to. So we knew that xn belongs to which bump, so we can calculate this, and the wj as well. That's point number one. Now, point number two, just flip this, right? If we knew these things, which is wj, mu j, and the covariance, if we knew this, then we know which point belongs to bump j, right? So we know which xn belongs to j, right? And so we're going to alternate this. So similar to k-means, we alternate these steps. And so let me write down the algorithm and then also talk about that latent variable that we were talking about. All right, so this like step one, and maybe let me write it on another slide. I hope I have enough slides, but that's fine, we can add. So now step one, initialization. What is initialization in this case? All right. Well, initialization could be random assignment or using k-means clustering, beginning from that. Begin with some clusters, assign points randomly, something like that. But for that assignment, we are introducing this new variable called gamma, and this is how this is denoted. So this is gamma n and j. What is this n and j? N is the nth data point and j is the jth bump. Okay, and so this is defined as the fraction. This is the fraction of data point xn that belongs to bump j. All right, so you must be like thinking, what do you mean by this fraction of a data point? So here we are taking it a step further. Remember earlier we were saying this particular point belongs to this particular cluster, or this particular point belongs to this particular bump. But now we are taking a step further and we are saying like this is not hard clustering anymore. So that referred, like in k-means, it was called hard clustering. One point can belong to one cluster only. And now we are like generalizing it, and we are saying we don't have to commit that a particular point belong to one bump only. The same point can belong to multiple bumps. It's just that there is some part of that point that belongs to a particular bump. Okay, mathematically speaking, think of this like gamma for any nj as like this part of this being like this has n rows and k columns. This has n rows and k columns, such that for any like row, this is x of n. So this can have like many values, and the sum of these, like this entire row, is going to be 1. This is what we're trying to say. So essentially this gamma n of j should be greater than or equal to 0, and the sum over j, right, the sum of this gamma nj should be 1. So the like overall throughout all the parts that it has in other maybe clusters should add to 1. It shouldn't go beyond that. But then this is how we are going to represent it. Every point can be part of different clusters. This is a generalization of clustering where like one data point is not exclusive to one cluster. And why are we doing this? We are doing this because this is probability estimation. So one data point may have been like overlapped by two different bumps. And so this gamma, why we are spending so much time on it? Because this is crucial to this algorithm, it's crucial to probability density estimation. Now let's see what we do with this. So initialization involves, I haven't started initialization, I started talking about this membership variable. We also called it membership, and the book refers to it as membership variable. So I'm going to stick to that. And now is the step 1. So what was this initialization? The initialization is that assume we know some gamma n of j. Okay. So now, because I know, or I begin with some random value, I know how much data belongs to my bump j, right? And so maybe think of that like how much data belongs to one bump j could be like one column here. Some column here is that data that belongs to some j, which this is like step 1, which I'm denoting by n sub j. And that is going to be the sum of n is from 1 up to n gamma n j, right? All right, so I know like how much data belongs to bump j. Now total number of data points can be denoted by using this n of j, right? So that would be the sum over all j's and n of j, right? Now using this, can I do something else? Because I have like two other things, in fact 3 other things to figure out, like the w's, the mu j's. Once I have these things, right, then what can I do? Well, I can calculate the w's, the mu of j, and the covariance, which was the sigma of j. And how is that? Let's do that here. All right. So what I'm going to do here is that I'm going to say the volume in every bump, which was volume in every bump, which is wj, is n sub j over n, right? Because that's like for one bump and this is the total. So that's how we can calculate that. The second thing that we need to calculate is mu sub j. Now, what is this mu sub j? This was, remember, the centers. And how do we get the centers? Well, if I can get all the data that belongs to bump j and divide it by the number of data points in j, because this was the average, remember? So all the data that belongs to bump j over the number of data points in j should give me this, which means I can have the numerator, which is all the data that belongs to bump j, is n is from 1 up to n, but then we have the latent variable, which was the membership, deciding membership of every data point multiplied by that data point. That's that. And then it has to be the sum of, or like, it has to be like 1 over n of j. Essentially, this can come out as well, and it has to be like outside the summation. So this is the average for some bump j. The third thing is the shape parameter. And how can we calculate that? Well, by definition, this is the average of outer product minus the mean of the outer product. And this is coming from or inherited from the definition of my Gaussian. And so I can calculate that by using 1 over nj. As I said, this is going to be n is from 1 up to n, gamma nj, x n, x, n, t. Why is the gamma coming in? Because I don't know the contribution of each of these. Of course, I know the definition of that, minus mu j t. That's it. So now, because from the definitions, I can calculate these 3 parameters. And I began by saying that I know this gamma. And then based on that gamma, I can calculate these parameters. So once I have them, I'm done with my step 1. So what is my step 2? Now here I have updated all the parameters. I knew gamma and j. I can update these parameters. Now I have to go and update my bump membership. Now update my gamma, because I have now these new values. And how am I going to update the bump membership? Now think about this bump membership. It's nothing but the probability density of my x of n, like the probability of where xn came from, like which bump it came from, divided by the sum of the probability density of like all the points from all the bumps. This is what this is, right? Let me actually write it down. So this is the probability density of xn came from bump j. That's how this is membership, right? And then this is the sum over all the bumps of this probability that xn came from bump j. I'm going to add them up, correct? And which in turn can be rewritten as, let me write it down first, wj n x n mu j this over the sum of this, sum over all j's, wj n x n mu j sigma j. So what is this? Like, what is this w? This w is the probability that a point is generated from bump j, correct? And this thing here, this n, and we've talked about it before, is the probability to generate that data point given some bump center, given some shape. And the denominator here is nothing but summing up the terms to get the entire probability density over all the curves, or all the bumps, right? We're not calling them curves anymore, so let's call them bumps. Now, once I'm done with like this step 2, all I have to do is repeat step 1 again, because now I have like gamma, and so I'm going to recalculate the other things and keep doing that until convergence. So step 3, I'm going to write here, repeat until convergence. When you don't see much change in your outcome, then that's it. And so these two alternating steps, they constitute something that's known as the expectation maximization algorithm. Well, this algorithm gives us really good results, but it doesn't necessarily go to global max at times. And that's like a small drawback, but it's most of the time shown to like give good results. That's the good thing about it. And basically think of this algorithm as like an excellent algorithm that bootstraps itself to a solution. All right, so let's look at this in action. And I think I had this, yeah, here. So I have this like written down in terms of like more logical steps, and this is taken from the book. So this is the EM algorithm, or the expectation maximization algorithm for GMMs. Start with the estimates of the bump membership, as I said, and then calculate the W's, the mu, the sigmas, and then given those, update the bump membership with those input and keep iterating until convergence. It's as simple as that. Now, as I said, we have to look at this in action, and let's look at that. Here it is in action. The left side is 10 center GMM, and as you can see, bumps are not as spherical as in Parsons. Like, they're more smooth, I would say, right? And why is that? That's because like we have these shapes that are determined by my covariance matrix, which was missing earlier. And so we have these like covariance matrices here deciding the shapes as well. So that's an extra parameter, I would say, added, but then we have ways to figure that out. The right hand side is showing us the density contours. Remember, red is high, blue is low. And the centers, like these black things here, are the centers. And the centers identify essentially clusters. All right. So as you can see that there is like we are able to figure out these smoother regions of higher density versus like these smoother curves around the smoother contours, showing us the segregation of low density regions with high density regions. And this, by the way, is a good technique and a very widely used technique in unsupervised learning. So this is it. These are the two techniques that we wanted to look at in under unsupervised learning, and this was, I would say, a quick peek at unsupervised learning. We just looked at two approaches, and we like using these two approaches, we kind of summarized what the fundamental idea of unsupervised learning is. We uncovered the fundamental idea behind unsupervised learning. Although this is not like enough, there is a lot more that you can go ahead and discover yourself. And because the textbook covers this much, and so I'm going to stop here. And next time we're going to begin with something that's really interesting, and let's see what that is. Thank you.